Welcome to the 328th presentation of the Wonders of Physics. Before the show begins, I want to assure you we make all of our demonstrations as safe as possible, provided you wash your hands and wear your masks. Because of COVID-19, we're not able to have a live show this year, but Professor Sprott has come up with a way to maintain the 37-year tradition of yearly presentations of the Wonders of Physics. I'll let him explain. And so here he is, from his laboratory at home, that homebound hermit, that masked master of mechanics, that wonder of physics, Professor Clint Sprott.
Welcome to the Wonders of Physics. I'm Professor Clint Sprott, and I'm not able to invite you to my laboratory this year because we're all sheltering at home. So we decided to let you help us put on the show. We invite you to make a short video clip in which you do some of the demonstrations we've used over the past 37 years. You can use materials you probably have at home. We'll take the best of your videos and edit them into an hour-long show to be shown around the world. We'll also offer awards for the best quality videos and the best explanation of the physics. We've provided a list of demonstrations from which you can choose, or you can think of your own. Please limit your video to about 2 minutes and send it with the submission form, which you can find on our website at wonders.physics.wisc.edu/contest, and check the webpage throughout the year for updates and results. Good luck and good physics.
That sounds like a great idea, but some people may need a bit more help and advice. Let's ask Mike Randall to provide some further guidance.
Hi, Mike Randall from the Physics Experience here. Today we're here to talk about the Wonders of Physics program, and particularly our annual shows, which we've been doing for 37 years, every February. But this year's, for obvious reasons, we're going to do things differently, and you can be involved. We're asking you to submit a 2-minute video demonstrating a physics concept. And awards will be given for the best videos, and winners will be posted on our website and edited into a longer video to be shown on public television. Now, if you're like going, physics? Really? Physics is hard. It's boring. No. You are physicists. You're really good at it. Everything you do is physics. And so pick a topic that interests you. It could be around sports. It could be around music. It could be around dancing. It could be around cooking. Really, anything. Pick something that you like to do and then look for the physics in that. And if you're still not sure, really how to go about that, there's lots of opportunities. So there's you can go to the Wonders of Physics website. That's wonders.physics.wisc.edu. You can also go to Professor Clint Sprott's website, and if you do a Google search on Sprott and the Wonders of Physics, you'll find it. There's also other opportunities. I have a YouTube page, the Physics Experience YouTube page, and even on our local TV station. I did a lot of programs over the years on NBC 15, so if you go to NBC15.com and do a search on physics, you'll see some demonstrations there, and also on their YouTube channel, which I believe is WMTV. Anyway, lots of opportunities. Make sure, of course, if you're 18 or under, that anything you do is you do it with your supervision of a parent or an adult guardian or your teacher, because they're going to be the ones who will have to submit the video for you, okay? Because we want this to be safe for everyone, and I want you to have fun with this. This, I think, is going to be a really great project, particularly for families to do during the pandemic, because it's like this is something you can do at home. You can record it on your own phone. Just mainly have fun with it. And now those submissions are due by June 30th of this year, so make sure you get those in. But I wouldn't wait. You could do it right away. And if you need more information, again, go to the Wonders of Physics website. That's wonders.physics.wisc.edu. Thanks so much. We look forward to seeing your video.
Thanks, Mike. That should get people working. While we're waiting for our first submission, let me show you this short video from my friend and colleague, Sam Shakasheri, congratulating us on the 38th season of the Wonders of Physics.
Congratulations, Professor Sprott, on the 38th anniversary of your wonderful program. I am so pleased that you have been doing this for so many years, and I look forward to watching not only this program, but future programs, all in keeping with living the Wisconsin idea in the 21st century. Congratulations, Clint. The person I would like you to welcome to my lab is the person that is well known in our community for the program that he puts on called The Wonders of Physics. Please welcome my friend, Professor Clint Sprott. Hi, Clint. Welcome to my lab again.
Now we're going to get down to brass tacks.
Oh, it brought me some brass tacks. Brass, of course, has zinc in it, zinc and copper.
That's right. You know, it's a special treat to share this 30th anniversary with you because you know it was exactly 16 years ago that I sat out in the audience here and saw you do one of these presentations for the first time, and that was the inspiration for the Wonders of Physics.
I'm glad that you did that, Clint. Really.
Here we have a bicycle wheel, except this is a little bit unusual because this bicycle wheel has concrete in it, so it's quite heavy. There's a lot of interesting things one can do with a heavy bicycle wheel. One interesting thing we can do is to stand up on a rotating platform like this. Well, not much is happening. In fact, I can't even make myself spin around very well, except if I take the bicycle wheel and spin it, it causes me to spin around. Now, if I take the bicycle wheel and turn it upside down, it makes me spin the other way.
You never know who shows up in the lab. It's Rocket Man. Oh, it's Professor Sprott from the Wonders of Physics. Hello, Clint. Happy to see you, Clint.
With this fire extinguisher, and let's see if I can make myself go around. Oh, I'm going around already. The floor must not be level. Now, you notice an interesting thing. When I'm going around, how do I stop? Oh, the other way. Good idea. This is actually an illustration of Newton's first law of motion. An object in motion will continue in motion until it's acted upon by a force. And here's the force. So let's try it the other way. And I can stop. Yes, it was Bassam Shakasheri who inspired the Wonders of Physics with his own Science is Fun program. And we've done many joint presentations over the years. And now we've received 46 videos from around the world. Our 9 judges have submitted their scores, and we're ready to announce the winners. All the winners will receive a plaque with their names on it, and they'll be able to choose from a list of 10 prizes. The first place winner will be announced at the end of this video, and so stay tuned. Meanwhile, the award for the best video about the physics of motion goes to Arnav Bali, a 13-year-old middle schooler from Connecticut. He shows us how to find and use the center of mass. See if you notice a slight error in one of his formulas.
Hello everyone, my name is Arnav. A few weeks ago, I noticed that I could never pick this ball up when I was standing against a fence, but it was very easy when I wasn't standing against the fence. So you might wonder, why is this? Well, it has to do with center of mass. If you take the average location of mass in an object or system, you get the center of mass. To find the center of mass, you can use this formula, which takes the mass of the object, multiplies it by the position of it, and then divides it by the number of objects in the system. To make it easier, if an object has a symmetrical shape like this lacrosse ball, then the center of mass is directly in the center of it. To see this in action, we can take this clear piece of plastic and mark the center of mass, which again is in the center of it. Now, if we place it anywhere on this table, as long as the center of mass, aka the dot, is inside this area of the table, it won't fall. But as soon as the center of mass gets outside the area of the table, it falls. That means the center of mass is where gravity is acting on the object. So you might think center of gravity and center of mass are the same. That is somewhat true. As long as the object is in a constant gravitational field, the center of mass and the center of gravity are in the same location. Here on planet Earth, the gravitational field is nearly constant, which means the center of mass and the center of gravity are in the same location. Though, remember, they are not the same thing. Now let's take a look at the ball again. This time I've marked the center of mass and the region of support on me. Immediately you can see that the region of support is from the tips of my toes to the back of my heel. Now when I bend down without the fence, you can see that my body naturally shifts my center of mass backwards to compensate for me moving forward. When I'm standing against the fence, I cannot do that, so my center of mass gets outside the region of support, and then I begin falling. To recap, the reason I couldn't pick this ball up when I was standing against the fence was because my center of mass was shifting outside the region of support, which made me fall to the ground. Thank you so much for watching, and I hope you learned something new.
Here's another video about the physics of motion by a brother-sister team from Wisconsin and winner of the best middle school entry.
I'm bored. What should we do, Maddie?
I know! Let's tell them about Newton's laws of motion.
Good idea. I love Isaac Newton. The first law.
An object at rest tends to stay at rest.
An object in motion tends to stay in motion, which we shall demonstrate. This ball is going to be the thing that is going to get in motion. See, by me pushing it, it starts its motion.
I am the force!
And the force stops it. The second law!
When an object accelerates, it's in relation to the object acting on the object.
Meaning that the object will continue going in the same direction that the action is.
We shall demonstrate this now.
Yeah, we did this before, and it was very fun. Do this at home. if
This
you want.
ball will transfer the energy to this ball.
And it'll make the ball
Shoot
go like
up.
that. The third law.
Every action has an equal or opposite reaction.
For example,
The air will shoot out of the balloon, and the reaction to the air shooting out will propel the balloon forward.
let's demonstrate. Thank you for seeing this video on Isaac Newton's laws of physics.
They are the foundation of modern-day mechanics.
The winner of the award for the best video from someone over the age of 50 goes to David Blau from our own University of Wisconsin-Madison for his experiments with the trebuchet.
I got really bored and frustrated during the pandemic. Being cooped up at home made me want to throw things, so I built a trebuchet. I used a design by a maker in Britain named Tom Stanton. A trebuchet is a medieval siege weapon similar to a catapult. It gets its name from an old French word that means overthrow, because it throws an object overhead. My trebuchet is too small to wreck any castle, unless it's a sand castle. It launches an object the size of a tennis ball. A trebuchet converts potential energy into kinetic energy. When we lift the weight into position, we put potential energy into the system. The force of gravity on the weight is the potential energy. When we release the trigger, gravity makes the weight move, converting potential energy into kinetic energy. A trebuchet uses a lever to provide mechanical advantage. The weight is on the short end of the lever arm. The payload is on the long end. When the weight drops, the payload end whips around the central pin. It travels a longer distance than the weight end during the same amount of time, giving the payload end a higher speed or velocity. The payload rests in a sling attached to the end of the lever arm. As the arm rotates, centrifugal force moves the sling outward, making the payload travel an even greater distance and increasing its velocity even more. The sling swings around the end of the lever arm like a pendulum until it detaches, flinging the ball forwards and upwards. The trebuchet is on wheels and rolls forward as the weight drops. This allows the weight to fall downward in a straighter line, increasing efficiency, and the forward roll gives a little extra momentum to the payload. We tried several different payloads with different weights. Some worked well, and others didn't. The heaviest payload was a light-up ball weighing 202 grams. It went backwards. We think it was too heavy to stay in the sling. We had better luck with a light-up ball that only weighed 39 grams. The baseball, tennis ball, whistle ball, and pinky ball all worked well. The golf ball went the farthest. It has little dimples on it that reduce drag. It traveled about 150 meters. We had fun experimenting with our trebuchet, but don't expect it to protect you during a zombie apocalypse. The zombies would have to stand in one spot a good distance away and wait patiently while you load it.
At the other extreme is our youngest award winner, 8-year-old Rowan Evanson from Wisconsin. He shows us how levers work. He sent us a 5.5-minute video, but here's a 30-second clip from his submission.
About to lift my dad with one finger. Watch me. Look.
No way.
Look, he's on
I'm
the ground.
pretty heavy. I don't think you...
Now he's off it. Easy peasy.
Whoa! Ah!
Well, I guess it was not actually magic. I was using a lever.
The next video is from a California high school student who received the award for the best video about the physics of oscillations.
We all know that when we're on the swings, we follow this continuous back and forth swinging motion. Or you might be familiar with hypnotizing someone, the pocket watch going back and forth and back, and phew, I almost got dizzy there. But if we break down the swinging pattern and see the physics behind it, we notice that this motion mirrors that of a pendulum. But what is a pendulum? By definition, a pendulum is a body suspended from a fixed point so as to swing freely to and from away under the action of gravity. Simply put, as an object travels upwards, it decreases in velocity until it comes to a complete stop at its maximum height, and on its way down, it continuously gains speed until it reaches its maximum velocity at its lowest point, or equilibrium. But let's convert this into energy. For this pendulum, energy can be characterized as either kinetic or potential. Kinetic energy is the energy possessed during motion, in this case corresponding with velocity. At the pendulum's maximum velocity, the kinetic energy is also maximum, and at the minimum velocity, the kinetic energy is also minimum. On the other hand, potential energy is the energy stored depending on its position relative to others. There are many different types of potential energy, but in pendulums specifically, we'll be looking at gravitational potential energy, which depends on an object's distance from Earth. For example, when we jump, we fall back down because Earth's gravitational field pulls us inwards. This energy transferred between the highest point and surface is gravitational potential energy. Another thing to know is that the total energy is constant regardless of position. The law of conservation of energy states that the sum of kinetic and potential energy will always be equivalent. For example, if I measured the total energy before dropping the weight, it would be equivalent to any point during its motion. Any change in either kinetic or potential energy will be offset by the other with an equal and opposite magnitude. Well, I hope that gave you a basic understanding of pendulums. Thank you for watching.
On the same topic, the following video from a group of East Troy, Wisconsin high school students received a $200 cash award from the United States Metric Association for the best use of the metric system.
We chose to do the energy unit, and in this presentation we discussed 3 different types of energy. Our title is Energy in Action.
All of our data and calculations are based off this video. Our first type of energy is GPE, and GPE is the energy an object possesses because of its position in the gravitational field. The formula is mgh, and we're defining the bottom of the ramp to be 0 height. So our mass of our student plus the scooter was 63.5 kilograms. The height of the ramp was 1.57 meters. We plugged those numbers into our GPE equation and got 980 joules.
So kinetic energy is the energy that an object possesses due to its motion, and the formula is 1/2 mv squared. But before we could find the K, we had to find the velocity, which is distance over time, which came out to be 1.72 meters a second. When you plug that in the KE formula, it's 93.9 joules. And as you can see on the bar graph, all the GPE was transferred over to kinetic energy. As you can see in the picture, the skater at the bottom of the ramp has maximum kinetic energy.
Alright, so the GPE result has to do with the law of conservation of energy. Energy can neither be created nor destroyed, only converted from one form of energy to another. So if there was no outside frictional forces acting on the system, then the skater would have gotten back up to the very top of the ramp. But since some energy was transferred to thermal energy and lost frictional forces, he did not make it quite all the way up to the top. Alright, so thermal energy is the last type, and this is the energy that gets transferred to the surrounding environment as heat. Our formula is the initial energy plus work equals final energy. So for our calculations, the initial energy was the same as GPE at 980 joules. And the final energy is going to be very close, but a little less than 980 joules because the initial height is just a little bit, or the final height that the skater got to is just a little bit less than the initial. So only a little energy was transferred to thermal energy due to frictional forces. And the wheel bearings in the scooter helped to reduce the friction altogether. And as you can see in our bar graph, some energy was converted to thermal energy.
The winner of the award for the best Rube Goldberg machine was Trey Wilson, a high school student from Florida. Her video included a long written explanation of the physics principles that we omitted in the interest of time. And our final award-winning video about the physics of motion came from a California high school student. It gives an explanation of the physics required for a journey to Pluto.
Want to go to Pluto? We've flown by, but I want to stop there. I just need to figure out how. Before you go to Pluto, you have to go to Mars. Then you have to get off of Earth first. But how? With a timely exploration. Copernicus claimed that the sun is the center of the universe. Brahe did not agree, so he built an institute on an island and spent decades carefully taking measurements. His assistant Kepler used this data to prove heliocentrism, ironically, and also discovered that the orbits of planets are elliptical, not circular. The planets don't move at the same speed, and the farther away a planet is, the longer it takes to go around the sun. Separately, Galileo experimented with motion, and Newton put all of these ideas together to theorize universal gravitation and the laws of motion. Okay, what does this have to do with Pluto? Have patience. Velocities, or speeds, change due to forces like gravity, and all things are affected by it. When you throw something in the air, it falls back down, and the velocity decreases. If you throw something faster, it travels farther, but eventually comes back down. But if you launch something at a fast enough speed, called orbital velocity, the object will always be falling, and as the Earth rotates, it never actually reaches the ground. This is how satellites orbit the Earth. So that's how one gets launched off Earth. Yes, and now to get to Mars, we use the Hohmann transfer orbit. If we increase the velocity, a spacecraft can leave Earth's orbit and orbit the Sun. Scientists timed this very carefully so the elliptical orbit it travels along meets Mars. Once there, the speed is decreased until the spacecraft is at the velocity that allows it to orbit the planet. And voila, we're at Mars. Brilliant! I just need to plan a Hohmann transfer to Pluto, and I'll be all set! Actually, that's not the case. To get to Mars, it usually takes about 8 months. To get to Pluto using the Hohmann transfer would take a lifetime because it's so far away. As Kepler found, the farther away a planet is, the longer it takes to orbit the Sun. Also, remember forces change velocities? The speed on this big orbit would be so fast that in order to slow it down, we would need an extremely powerful rocket to apply that force, and we just don't have that power. Oh, so that's why New Horizons flew by Pluto without stopping. But why explain all this history if it's impossible? Because the farther back you look, the further forward you're likely to see. After 200 years, Newton's theories were challenged by Einstein, and even today we're still trying to grasp the workings of a universe. Who knows, you may just find a way to go to Pluto and beyond. Thank you for watching.
Now a bit closer to the Earth, The next video from a high school student in Bangladesh won the award for the best video on the physics of airplane flight.
YSICS, physics. What do you mean by physics? Well, it's the way the universe works. How do you think a gigantic airplane flies over the sky with a weight of around 90,000 pounds and not even falling down right here on the ground? Well, what makes it fly and keeps it flying both are nothing but physics. To demonstrate the physics here, we can assume four forces that work together to make an airplane fly. First of all, thrust, which makes the airplane to move forward. Secondly, drag, which is caused by the collision of the airplane's body and the air molecules it passes through. Actually, it pushes the airplane backward. You can even feel this force by moving your hand rapidly. And then it comes weight. It's the downward force caused by the weights of the passengers and the airplane itself. And then lift is the most important force here, which moves the airplane upward and allows it to fly. So it's obvious that when the lift is greater than the weight, the plane will fly. Now how will you increase the lift that higher to make an airplane fly, right? Actually, this is where the term airfoil comes into play. All the wings are made in the shape of this airfoil, which plays the crucial part in the flight. When the airplane is not moving, the air molecules exert the same pressure both at the top and the bottom of the wing, and that causes no lift. But when the plane moves forward, the curve shift and the angle of attack cause the bottom of the wing to collide with more air molecules than the top. Moreover, the upper air molecules move faster than the lower air molecules. According to Bernoulli's principle, when the speed of the fluid increases, pressure decreases, and when the speed decreases, pressure increases. This means while moving, the air pressure of the bottom goes up and the air pressure of the top goes down, and thus the lift is much greater than the weight and the airplane can fly. Let's have a real example. Wait, what I'm doing here in Africa, is that a lion? Oh boy, come on, come on, come on. Excuse me. Now we are doing this experiment with our own handmade airfoil and a fan by holding it like this against the air. You can see that I'm not even grabbing the airfoil, but still it's not falling down. Rather than it's pushing me upward to make a fly, and that's how an airfoil works. In the case of an actual airplane, the engine passes a lot of air molecules backward through the fans, which is enough to make the lift higher. And when these all physics and technologies interact properly, the plane finally flies.
We had a number of nice videos about the physics of sound. This next submission from students at East Troy, Wisconsin High School on the Doppler effect won the award for the best physics of sound video.
You may be wondering what is going on here. It may look silly and out of place, but we are actually studying the Doppler effect on sound.
What is the Doppler effect, you may ask? The Doppler effect is a change in wave frequency caused by movement of a sound source or observer. This causes the pitch of the sound to appear higher or lower depending on which way the sound or the observer is moving.
This is how sirens on police cars, fire trucks, and ambulances work. When they are coming towards us, the sirens are super loud, but after they pass us, you can barely hear them.
Looking at this diagram, you can see how the waves are stretched and compressed at different times. As a sound source moves towards the observer, the waves get compressed, and as the sound source moves away from the observer, the waves get stretched out. When the waves are compressed, there is a higher frequency. Higher frequency equals higher pitch, and low frequency, like when the source is moving away from the observer, means lower pitch.
As you can see, the Doppler effect is all around us. Next time you go outside, listen to the sound of the cars as they pass you. Or, if you get lucky, pay attention to the siren of a police car, because I guarantee you that now you can figure out which way the car is moving.
And from another high school in Neenah, Wisconsin, this group won the award for the best video about the physics of waves.
Hello, fellow physics enthusiasts. Today we're talking about the Rubens tube. The Rubens tube is a large metal tube with holes across the top. It's sealed on this side. Flammable gas is pumped in through there and has been lit to create a row of tiny little pilot lights across the top. Now, What's interesting about the Rubens tube is when sound waves are applied, using this speaker here on this side, the waves create pressure differences with the gas inside the tube, which affect the heights of the pilot lights. With certain frequencies of sound, they can create some pretty interesting effects. Ellie, tell us about that.
Your typical transverse wave will look like this and continue on. However, if it is bounded on both sides, then it will reflect directly over like so, and back over the same wave to create a standing effect. These places here with maximum vibrations are called antinodes with constructive interference, and here are the nodes with destructive interference and minimal disturbance.
Yes, so that's exactly right, except with the Rubens tube, sound waves are actually compression waves, which means that the gas molecules are compressed and decompressed in a motion that is parallel to the direction of the wave across the tube. So, when I play this standing wave frequency, that is for this length of the tube, the antinodes, where the tall flames are where the gas is going from compression to rarefaction, and the pressure differences create taller waves. Now the nodes are where there's no pressure differences and the flames remain small. And that is how you can visualize standing waves with the Rubens tube.
And our last video about sound is from Northeast Wisconsin Technical College. It won the award for the best capstone project.
Duh.
Hi, I'm Maddie, and this is Paige, and we'd like to introduce our capstone project from our Laboratory Science Technology program at Northeast Wisconsin Technical College. But before we get to this, we got to get to the science behind the table.
As energy travels through a medium, it creates a wave. There are two types of waves. The first is a transverse wave. As the wave moves, it creates points of high and low, which is the crest and the trough. From one point of the wave to the next is created one wavelength. And from the rest position to a crest, it's the amplitude. Most waves move through a solid medium, traveling this way. The next type of wave is a longitudinal wave. It creates different points of compressed waves, which is the compression, and as it separates, it creates points of refraction. And this is how sound waves travel through a wave. So let's look at how these waves look on a slinky. First, we can do the transverse wave, and you can see the higher points of the crest and the lower points of the trough as it moves through the slinky. And next, we can do the longitudinal wave, and you can see that the darker shadow parts are the compression, where the regular parts are the rarefaction.
When the wave hits a solid barrier and the energy goes back the way it comes, it produces a standing wave. The node is where those waves then intersect, and the antinode is where those waves are farthest apart. Now let's study these with the help of a string and a drill. Here we see the antinode where the waves are farthest apart, and up here we see the node where the waves intersect each other. This is how our table works. We turn the gas on and they travel up this tube into the table, where we then place the speaker into the speaker housing unit and then place the membrane on top of that speaker. We've then placed the speaker housing unit onto the bottom of the table and turn on the music. It then sends sound waves into the membrane, and the membrane sends those sound waves into the gas chamber, and then the pressure from those sound waves send the flames up to the top of the table.
Used to keep it cool, used to be a fool, all about the bounce in my step.
We had only 2 submissions on electricity, and they both won awards. The first was from a group of high school physics students from Neenah, Wisconsin. It was the best video on the physics of electricity.
This is what we call the Harry Potter trick, but there's no magic involved here. It's just physics. What Lindsay is demonstrating here is called electrostatic levitation. This works by creating an electric field to levitate a charged object. Here we can see Lindsay charging the PVC pipe and the plastic bag ring. Since we know that opposite charges attract, we can assume that the same charge will repel. In order to explain what is happening that would make these charged objects repel, we need to take a closer look.
It all comes down to the electrons. Electrons are subatomic particles that have a negative charge. Both of these objects start out with neutral charges, and through a process called triboelectric charging, electrons are transferred from one material to another. This transfer is determined by the electron affinity of each material. The PVC has a stronger electron affinity, so it'll attract more electrons and then have a negative charge. Its exact electron affinity is on the board. The fur, on the other hand, has a weaker electron affinity, so when the 2 materials are rubbed together, the friction generated will cause the objects to charge. This is the Harry Potter physics magic that makes this trick possible. The man behind the physics magic of Harry Potter is known as Coulomb. Coulomb had 2 laws that we'll focus on today. His first law states that like charges repel, while opposite charges attract. This is important in the Harry Potter trick because we have 2 objects that repel, so they need to have the same charge. His second law states that the force that is exerted between 2 charged objects will be directly proportional to the size of the combined charges and inversely proportional to the squared distance between them.
And now, thanks to electrostatic levitation, you are ready to attend Hogwarts.
The second electricity video from a high school student came all the way from India. It won the award from the best video about the physics of lightning.
Lightning is best formed in a hot and humid climate. Most of the formation of lightning takes place within a cloud. It is caused by the downdrafts and updrafts of thunderstorms. The cold air containing ice crystals and the warm air containing water droplets converge. When both meet, the water and ice bump together, causing static electrical charges. The electrons are transferred to the heavier particles and they develop a negative charge. The lighter particles, upon losing electrons, develop a positive charge. The updrafts carry the lighter particles to the top of the cloud and the heavier particles fall to the bottom of the cloud. When the positive and negative charges grow long enough, an electric field is induced. The positive and negative charges act like the opposite poles of a battery. The negative charge at the bottom of the cloud is attracted to the positive charge on top of multiple clouds as well as the crown of the earth. Even then, the electric current does not flow smoothly between the 2 poles since air is not a good conductor of electricity. The objects on the ground emit positive streamers in reaction to the negative ones given out by the clouds. This seems to be only one flash, but is actually a series of return strokes of electrical energy reaching back up into the clouds. The 2 connect to make a path for the electrical current to flow through. The path of lightning reaches temperatures of around 50,000 degrees Fahrenheit. This heat causes a booming sound as excessive pressure in the lightning path expands at supersonic rates on return strokes. Lightning strikes are the ones that heat up to extraordinary temperatures and last for even lesser than a second. This was how lightning, a powerful electrical discharge made during thunderstorms, is formed.
We had several nice videos about the physics of light, 2 of which, both from East Troy, Wisconsin high school students, won awards. The best video about the physics of light was on Newton's rainbow.
Have you ever wondered why the colors on the rainbow are the way they are? Why red is on the top and violet's on the bottom? Well, during the late 1660s, Newton started to experiment with color. During this time, people believed color was a mixture of light and darkness, and that colored light was solely seen from prisms. Newton discredited this idea by placing a prism near a window that projected a spectrum of light. He continued to discredit the theory more by refracting the light back together. From his observations, Newton proved that light alone was responsible for color. We, as humans, can only see a small portion of the electromagnetic spectrum. We can only see between 400 and 700 nanometers, which is called the visible spectrum. The visible spectrum is the 7 colors of light. Different colors have different wavelengths. For example,
Red has the longest wavelength at 700 nanometers, and violet has the shortest wavelength at 400 nanometers. Because red has the longest wavelength, it bends the least, which is why it's at the top of the rainbow. As you go down the rainbow, the wavelengths of the colors decrease as the bending of the light increases. When you reach the bottom of the rainbow, you come across violet. Violet has the shortest wavelength, which results in the greatest bending. You can see this by creating your own rainbow with a hose. The first step is to stand in a spot where the sun is behind you. Next, you put your thumb over the hose nozzle so that the water creates a spray when it comes out. And lastly, you hold the hose out in front of you and look for the rainbow. As you can see, red is at the top of the rainbow, bending the least, and violet is at the bottom, bending the most. Now, hopefully you're able to better understand why rainbows look the way they do.
The second video about light from East Troy, Wisconsin High School was given the award for the best video from our home state of Wisconsin.
Here we have a petri dish of clear gelatin and a red laser pointer.
Let's see what happens when we shine the laser pointer through the gelatin. That's refraction. Light refraction is the change of light's direction when it changes boundaries between mediums. Light travels slower through the gelatin because its index of refraction is higher than air. This causes the light to bend.
What's the index of refraction?
It's a ratio of the speed of light in a vacuum over the speed of light through a different medium. This variable is represented by n. This definition of n helps us understand Snell's law of refraction.
What's that?
Snell's law states that the index of refraction of material 1 times the sine of the incident angle is equal to the index of refraction of material 2 times the sine of the refracted angle.
Now what the heck does that mean for somebody not in a physics class?
Think of it like this. When you roller skate, you travel the fastest on a less dense material like the road. If your left skate slipped onto a more dense material like grass, it would slow down while the right skate was still traveling quickly on the concrete. This causes the right skate to turn toward the boundary between the grass and the road. Light works the same way when it changes its medium from air to gelatin.
Whoa, that's really cool. Who knew light could change directions like that?
Yep, it's all around us, in water, camera, and even our eyes.
I hope you learned something today. Thanks for watching.
We had very few videos about modern physics, by which we mean things that have been discovered in the last 100 years or so. But here's a slightly technical one on wormholes and time machines from a high school student in Azerbaijan. It won the award for the best modern physics video.
What is the first thing you see when you look at my glasses? A bow tie, infinity, or maybe a wrinkled wormhole? A wormhole, also known as Einstein-Rosen bridge, is a tunnel connecting two places in space at different times. Similarly, I have two wrinkled duck heads here as a shortcut that consists of two mouths and a throat. No wonder wormholes can be too short sometimes. Here's a picture of me struggling to get through an extremely short one. In order to create a wormhole, we need to reverse the curvature of space-time, meaning the energy density must be negative for this. As the wormhole grows, gravity gets jealous and tries to close it. To keep it open, we need a matter with negative mass but positive pressure, like exotic matter. It's a super duper powerful matter you won't find anywhere. So how wormholes look like by the amount of it? More exotic matter, little exotic matter, and less exotic matter. A wormhole is traversable if it contains exotic matter. Then, if we can find it, is it possible to travel?
Here
we put a firecracker in the middle and detectors at the mouth. In the first case, flash reached the mouth at equal times, up to 2 seconds, and the path frame defined a light cone which is symmetric. If you slide it forward by 1 second, the mouth will be asymmetric and the light cone is tilted. This means that time is different between two maths. Like so, right now the Einstein-Rosen bridge as short as it can be. As time goes rapidly forward, the horizons start to separate and leave between them a region of space. Eventually, Einstein-Rosen bridge grows. Therefore, you have to move faster than the speed of light to get through it. The bottom part of our universe is sliding rightward, while the top remains at rest. According to the universe, the wormhole moves relative, but as seen through the wormhole, tunnels are resting to each other. Sadly, these tunnels are way too small for a human to pass through. But here's where the time machine comes into picture. We let a firecracker go off at time 2 seconds. It moves to the right mouth where it added mirror to reflect it into wormhole. Flash passes through the wormhole and arrives at time 0 before it went off. In other words, we have a time machine. In general, the idea of wormholes comes from the fact that nothing is perfectly flat or solid, like my ducks. If you look closely enough at anything, you will find holes and wrinkles in it.
And now we're ready to announce the first place winner of the 2021 Wonders of Physics video contest. That award goes to Alex Lee, a 16-year-old high school student from California, for his video on the rotational world.
Mechanics helps us understand how and why objects behave the way they do when they are in motion. We can study an object's movement translationally, like from one point to another, but what about rotationally? There is a whole different world within the physics of mechanics, the rotational world. All rotating objects have a property called moment of inertia, or rotational inertia, which is a quantity that describes how much an object resists the change in rotational motion. The more rotational inertia an object has, the harder it is for it to change its angular velocity. An object's moment of inertia is determined by its mass and how that mass is distributed. If there is more mass farther from the object's axis of rotation, then it would have more rotational inertia and will be harder to rotate. But if there's mass closer to the axis of rotation, then it will be a lot easier to rotate since it has less rotational inertia. Certain shapes, such as cylinders, rods, and spheres, have their own special equations to calculate their rotational inertias that can be derived using calculus. Another important concept of rotation is torque. Torque is the measure of how effective a force makes an object accelerate rotationally. Newton's first law states that in the rotational world, an object at rest will stay at rest, and an object rotating at a constant speed will stay rotating at that speed unless acted upon by an unbalanced torque. The net torque is equal to the inertia of the object times its angular acceleration. So if a torque is applied, it will change the object's angular velocity and accelerate. The effectiveness of a torque depends on three things: the amount of force being applied, the angle at which it's being applied, and how far the force is being applied from the axis of rotation. A force applied perpendicular to the surface and farther from the axis of rotation will produce a greater torque. That is why door handles are on the far side from the hinges. It is a lot easier to open a door from there since it produces a greater torque, causing it to accelerate and open faster. Lastly, angular momentum is important to the world of rotation. It is a quantity that describes how much angular motion an object has. The amount of angular momentum that a rotating object has is determined by its moment of inertia and its angular velocity. In a closed system where there are no external torques, the total angular momentum is conserved. Since angular momentum is proportional to the moment of inertia and angular velocity of an object, if one increases, the other has to decrease in order to keep angular momentum conserved. For example, if I am in a spinning chair and I lower my rotational inertia by pulling in my arms closer to the axis of rotation, my angular velocity must increase to keep the angular momentum constant. But if I bring my arms back out, then I will spin slower. With the COVID-19 pandemic, new difficulties arise and our daily problems become ever more apparent. However, if we look at the universe through a different perspective, we can open our eyes to new discoveries. We can figure out a way to solve these problems with our knowledge of science. So let's get the ball rolling and change our everyday world together.
Congratulations, Alex. You'd make a great teacher and a great physicist, not to mention a pretty good soccer player. We also have an award of a $200 gift certificate from Pasco for the teacher whose students sent us the most high-quality videos. That award goes to Kristen Mikowski from the East Troy, Wisconsin High School. Congratulations, Kristen, and to all your talented students. Now, there were many other excellent videos, but we had to limit the awards to the best of the best. I want to thank everyone who submitted a video to the contest. We started this contest to continue the 38-year tradition of presentations of the wonders of physics. But COVID-19 prevented us from having a live show this year. However, we hope to return to live shows next February. The contest was a great success and an excellent learning experience for the many students and others who submitted videos. So, we plan to repeat the contest next year. Look for an announcement in January and join the fun by submitting a video of your own. I hope you've enjoyed this 328th presentation of the Wonders of Physics. And with that, I thank you all for watching.